This is called the second transition curve. And this point, this ED, this is called the circular curve. This is the simple circular curve. Now, T1 is the starting point of the combined curve and T2 is the ending point. You can also say that T1 is the starting point of the transition curve and E is the first junction point. That is where the first transition curve ends and the circular curve. Then the D point, that is the point where the circular curve ends. This is the second junction point. This is the point where the circular curve ends and the second transition curve it begins, right? Now, this delta is the deflection angle, I is the angle of intersection, right? Now, shift, what is shift? Shift is basically the distance through which the circular curve is reduced if we point the transition curve. That is the shift. And delta minus 2 phi is the central angle for your circular curve, and phi is the spiral angle. That is the angle that half the length of the transition curve subtends at the center. So these are some basic notations. Some of these are similar as the previous ones. Few are new things like the shift and the spiral angle. And if you have any query, you can just text it. Okay, let me end that. All right, these are the notations that I already told you that. Now, for a transition curve to be an ideal, the fundamental condition is that the radius of the curvature should be inversely proportional to the length. Such a curve is also known as true spiral or clothoid. Okay, ji. Then we have the equation for setting out the transition curve. For that, you can use either the coordinate method or you can use the deflection angle method, right? So we will be using this equation by alpha is equal to 573 L square over capital RL, where small l that is the length of your transition curve, capital R is the radius of the circular curve. We know that there is a circular curve in the center, and capital L that is the length of your overall length of your transition curve. The small l is basically the length of that particular segment for which you are calculating the deflection angle. We will see this in a moment. No, there are different types of transition curve like Euler spiral, cubical spiral, and these are the corresponding equations for these particular types if you want to set them out. Now, characteristics of transition curves in that first is how can we calculate the length of the transition curves. So there are three different relationships. You can use any of these three depending upon which sort of data is available to you to calculate the length of the transition curve. First one is by adopting a definite rate of super elevation, right? Uh, let's say if you are given the rate of super elevation, then you can use this particular data. For this data, the length of the transition curve that will be equals to capital L is equal to n into h by 100. Okay. Over here, h is the amount of the super elevation in centimeters. Now, n is the rate. For example, its value can vary from 300 to 1000. Suppose let us do this example. Calculate the length of the transition curve required in order to attain a maximum super elevation of 15 centimeter, right? H value is 15, assuming the rate of super elevation to be 1 in 400. 1 in 400 means that for each 400, let's say 400 feet, if you move horizontally, then vertically you will travel a distance of 1 feet, right? So over here, the value of n is 400, h is 15. So just put the values over here. The length of the transition curves, that will be capital L equals to n is 400 and h is 15. So just put the value over there. So length of transition curve comes out to be 60 meters. So this is the first in which you are given a certain rate of super elevation, then you can use this particular relationship. The second is by considering arbitrary time rate of super elevation, right? Uh, so for that, the relationship is L is equal to H into V over X. ठीक है जी? Uh, H is the amount of super elevation and V is the velocity, and X is the time rate in centimeters per second, and its value varies from 2.5 to 5 centimeter per second. Again, there is one example. Let us calculate the length of transition curve required in order to attain a maximum super elevation of 15 centimeter, right? H value is given to you, assuming a rate of super elevation of 3 centimeter per second. X value जो है वो 3 centimeter per second. The speed of the vehicle is 50 kilometer per hour. Okay, you are given the speed of the vehicle in kilometer per hour. You need to convert it into meter per second. For that, you need to multiply it by 1000 and divide by 3600. So just put the values over there, and you have L equals to 69.44. So this is the second criteria in which you consider the time rate of super elevation. The third is by considering the rate of radial acceleration. And for that, the relationship is L is equal to V cube over KR, where K is the change of radial acceleration, and it has to be in meter per cubic seconds. And then there is one example for this as well. Let us calculate the length of transition curve when the rate of radial acceleration is 30 centimeter per cubic second. Allowable speed, that is 60 kilometer per hour, and the radius of the curvature is circular curve is 200 meters. So first of all, you need to convert the speed into meters per second, right? And then the key value that has also be in meter per cubic second. So just convert that and put the values over there, and you can calculate the value of the L. Now these are the three criteria. You can use any of these three uh, relationships depending upon which sort of data is available to you, and you can calculate the length of the transition curve. Now we will see that now shift. I told you earlier that shift is basically the distance through which the circular curve is reduced if you provide the transition curve, and the relationship for that is kept L square over 24R is given over here as well. You can see that this one, this L square over 24R, where L, capital L, that is the length of the transition curve, and R is the radius of your circular curve. These elements of combined curve, we have already discussed this thing that now we will solve a numerical. Uh, this is basically a flow chart that the steps that you need to follow if you want to calculate the required data of transition curve. Uh, so first thing is the length of the transition curve that can be calculated from either of the above three formulae. Uh, so he has considered the rate of change of radial acceleration L is equal to V cube over KR. You can use any of the above three ones depending upon the type of data given to you. The second is the shift of the curve, that is L square over 24 hour. Over here, L is the length of the transition curve and R is the radius of the circular curve. Then you need to calculate the length of the combined curve for tangent, and for that the relationship is R plus S. tan into delta by 2 plus L by 2, where R is the radius of your circular curve, S is the shift, delta is the deflection angle, and capital L is the length of the transition curve. And then the spiral angle, that is equal to L into L over 2R. In order to convert it into degrees, multiplied 180 by 5. So then center angle for the circular curve, that is equal to delta minus 2 phi. And if you want to calculate the length of that, you will be using this thing. So length of the circular curve, that comes out to be pi r delta minus 2 phi by 180 degree. Then we have length of the combined curve. We know that it's a combination of two transition curves and the circular curve in the center. So capital L, that is the first length of the transition curve, plus pi r delta minus 2 pi by 180, that is the length of the circular curve in the center, plus L, that is the length of the second transition curve. So this is the combined length of the uh, combined curve. Then we have the change of the commencement of the curve, that is the starting point of the curve, that is T1. That can be obtained by change of, if it can be more clear from this figure, the change of the starting point T1, that will be equal to the change of the intersection point minus this combined tangent length. And then if you want to obtain the change of the first junction point, that is E1, that will be equals to change of this starting point T1 plus length of first transition curve. And the change of second junction point E2, that will be equals to the change of uh, this first junction point, this point, plus the length of this circular curve. And then the change of E2, that is the ending point of the curve, that will be equals to change of second junction point, this E2, plus the length of this second transition curves. And then you need to lay out the curve by using the, if you want to use the deflection angle method. For that transition curve, the relationship is alpha is equal to 573 L square over capital R into capital L, that you can see over here, this thing. In order to calculate the deflection angle for the transition curve, the relationship is 573. This is L square. By mistake, it is written over here as L cube. This is L square over RL, and this will give you the values in minutes. Right? And you need to convert it into degrees, minutes, and seconds. The second, if you want to, and the check over in this case is that the total deflection angle should be equals to 1 by 35, right? If you want to use the rectangular coordinates, then the relationship is y is equal to x cube over 6RL. No, for setting out the circular curve, it's the same thing that you have been doing so far in case of simple circular curve, then you did it in case of combined curves. And if you see the reverse curve, it's also the same thing, that you just have to lay out the two circular curves in the opposite directions. Okay. Now, just going through that, now we will be using we will be solving one example, so that further if there is some misconception, then it gets cleared over here. Okay, ji? In the meanwhile, let me just check your messages if you have anything asked over there. Okay, some of you are saying that you just obtained the link quite late. Okay, we will be going through this example, and the things, they will get clear to you over here as well, right? So the example is two straights AB and BC intersect at a change of 1000 meters, the deflection angle being 40 degree. So the value of delta is given to you. It is proposed to insert a circular curve of radius 300 meters. So the radius of the circular curve, that is given to you, R value is 300, with a transition curve of 90-meter length at each end. So the length of the transition curve, it is already given to you, right? So no need to calculate it. Let us calculate all the necessary data for setting out the curve by the deflection angle method, taking a peg interval of 20 meters, right? We prepare the setting out table, taking the least count of the theodolite as 20 degree. I hope now this thing should be clear to you already, this least count thing and the setting out table. So just going through that steps. So first step is to calculate the length of the transition curve, but that is already given to us, so we can skip that part. Okay, the one question is that why is the transition curves on the opposite sides of the circular curve? It should be in between straight curve and circular. I think some of uh, transition curve, one of you has asked that why the transition curve is on the opposite sides of the circular curve. It has to be provided on the opposite side for the smooth passage from the road to the circular curve, right? So that's why it is provided on the both sides of the transition curve. Actually, the second step is to calculate the shift of the curve. Since the length of the curve, transition curve is already given to us. For that, the shift of the curve, the relationship is capital L square, that is equal to capital L square 24R. Uh, Capital L over here is the length of the transition curve, that is 90 in our case, and the radius of the circular curve is 300. So the value comes out to be 1.125 meters, right? And then is the combined tangent length, that is equal to r plus s into tan delta by 2 plus l by 2. Over here, delta is your deflection angle, that is 40. R is the radius of your circular curve, and s, that is the shift, that is 1.125, and l is the length of the transition curve, that is 90 in our case. So just putting the values over here, and the tangent length, that is combined tangent length, comes out to be 154.6 meters. Then we have the spiral angle, and that is L over 2R. In order to convert it into degrees, multiplied by 180 by 5. So the value comes out to be 8 degree and 36 minutes. The central angle, that is equal to delta minus 2 phi. Just putting the values, delta is 40, and spiral angle is 8 degree and 36 minutes. So the value comes out to be 22 degree and 48 minutes. Then we have the length of the circular curve. So using the pi r delta minus 2 over 2 phi over 180, the value comes out to be 119.38 meters, right? So this is for as far as basic elements. Then we need to calculate the changes. The change of the first tangent point, that will be equals to the change of the intersection point minus the tangent length. So the change of the intersection point which was given to us was 1000. So minus tangent length 154.6. So we have 845.4 meters. Then we have the change of the first junction point, that is where the first transition curve ends and your circular curve begins. So that is equals to change of the starting point plus the length of the transition curve. So the change of this starting point, that is 845.4 that we have calculated, plus 90 is the length of the first transition curve. So the value comes out to be 935.4 meters, right? The next is the change of the second junction point. It is a point where your circular curve ends and your second transition curve begins over there. So that is 1054.78 meters ultimately. Then the change of the second tendency point, that is the ending point of the curve. So that will be equals to the change of second junction point plus the length of the uh, second transition curves. So that comes out to be 1144.78 meters, right? Now we need to calculate the deflection angles for the transition curve, right? Uh, so for that, we know this thing already, that first we provide initial support in order to make the change a round figure. So since our starting value is 845.4, so in order to make that a round figure, the next round figure that comes to our mind is 850. We can also take 860 as well. As remember that we have already discussed in a number of times that how can we make the change a round figure. Uh, so 850 is the minus 845.4. So the length of the uh, first chord that comes out to be 4.6 meters. Then distance of second point from the first tangent point, that is we know that the peg interval is 20 meters, so let's keep on at 20. So that is 24.6. And then distance of third point from the first tangent point, that is 24.6 plus 20 again, and this will continue till we will be reaching a total length of 90 meters. Now one thing important over here is that that is different from the previous practice, is that in case of circular curves we were calculating the lengths for the individual segments, that is for the initial subchord and then for the final subchord and then for the full chords, and then at the end we were accumulating the angles. But over here we are taking the cumulative distance, right? And then there is no need to calculate the cumulative angles. You will see this in a while. Now deflection angles for the first point alpha 1, that will be equals to 573, that is the part of the relationship, into small l. Now small l is the length of the segment. For the first segment it is 4.6 square divided by capital R into L. Capital R is the radius, that is 300, and L, capital L, that is the length of the transition curves. So just putting the values over there, and you are having the angle as 0 degrees 0 minutes and 27 seconds. And deflection angle for the second point alpha 2, that will be equals to 573 now into this next value, that is 24.6. so this value, so just put it over here and you have the value 0 degree 12 minutes and 50 seconds, and this will continue till you will be reaching at this point. For this you can calculate the deflection angle 573 into 90, the square divided by 300 into 90, and the value is 2 degree 51 minutes and 54 seconds. Now we need to apply the check. The check is that total deflection angle should be equals to 1 by 3 5. So phi value is 8 degree and 36 minutes. So taking 1 by 3 of that, the answer is 2 degree and 52 minutes. So this is exactly our value that we obtained at the, and this value 2 degree total deflection angle 2 degree 52 minutes. So this is equal to 1 by 3 5. So this is also our check. If you want to check that whether your calculations are correct or not, you can apply this and see that if it tallies with one another. If it tallies with the one another, then your calculations are correct. Otherwise, you must have committed some mistake. Then is we need to prepare the setting out table for the transition curve. For that, the first point is column is the point, that is T1. The second is the change. Third is the chord length to be measured. Then we have deflection angles, and then angle to be set. Remember I told you that there is no need to calculate the cumulative deflection angle because already we are taking the cumulative lengths. Now the first point T1 and the change of the starting point which we calculated was 845.40, right? And then we have the chord length to measured, and that is this third column. Then we have deflection angle and angle to be set. The first point is the change is 850, right? This is over here. As you can see, we set this value as 850 in order to make that a round figure. So that's why 850 is over there, and the length comes out to be 4.6, and this is the corresponding deflection angle. For the second point, the change can be calculated by just adding 20 to the previous value. So 850 plus 20, that is 870. Then for the third point, plus again plus 20, 890. For the fourth point, again you need to add 20. So this will continue till the end of your transition curve. Alright, see, and then this is how you can prepare the setting out table and angle to be set. This is the same as the previous practice. That will depend upon the least count of your instrument. Since the least count of the instrument is 20 degree, right? So the first value is 0 degree, 0 minutes and 27 seconds, right? Now we know this thing that our instrument will not be able to read this 27 seconds, so we need to make it a round figure. So since the value is less than half, so you can round it to 20. And for the next thing, it is 0 degree, 12 minutes and 50 seconds. Again, 50 seconds. Either you can make it as 0 degree, 12 minutes and 40 seconds, or you can round it off to 0 degree and 13 minutes. So it depends on the individuals. So this is how you will be preparing the setting out table for the transition curves. The next is you need to prepare the setting out table for the circular curve. Now this you have been doing so many times in the previous lectures, so I don't think there is a need to go through this because you already know this thing. No, there must be some queries from your side. So if you have any query, then you can ask. G. G171, you can ask now. So this is the transition curve, right? Now I will give you one assignment. You will have to prepare this. जी
सर
देखिए बोले
तो सर सेक्शन डी से हूँ सर मैं, और सर सेक्शन डी ने सर अभी ज्वाइन किया क्योंकि सर अब लिंक लेट मिला है, वो इसलिए कि सर वो जिसके पास लिया है सर उसका इंटरनेट प्रॉब्लम था।
अच्छा जी